before I actually start replacing the capacitors in this RC1024 radio, now that I have picked a new multimeter, I would like to do a couple of things. One is I want to fill out a chart like this of the resistances, just like I did on the Watterson radio that I have decided not to continue with, partly so that I'll know where I need to check for additional problems, and partly because when you're replacing capacitors, it's a good time to also replace any resistors that are out of tolerance as well, and so this resistance information will come in handy there. You may see a device down here, which I'll talk about in just a second, that I built to help me do that. But before I do that, I would like to show you another set of YouTube videos on this same radio. Here is the first in a set of, I think it's 4 or 5 videos on the RCA Victor Arce 1064 by Jim Lindenaas. I hope I'm pronouncing that close enough to correct. He does a number of radio restorations on YouTube, and you'll recognize this is the same radio that we're working with. His cabinet is in a good deal better condition than mine. It doesn't have all those white paint spots. But I recommend that you look at this. He restored this radio, and it's another way, another look at restoring a radio like this. I said I would mention this box that you see sitting down here. Notice it has a rotary switch with, it says 10 positions. Actually, this switch is a 12-position switch, but I'm only using 8 of them. And I'll show you the wiring diagram of this in a second. You notice that a set of color-coded wires are coming out of here and going over to a tube base, and the 50L6 is plugged into that tube base. So what's going on there? Well, this tube base is made up of a top, which is just an octal socket, and a base, which is an octal tube base, connected together. And then what I did is I drilled a series of holes around the outside here, lining up with each of the pins, and connected wires from the top through to the bottom and also out the side. And then those wires that come out the side are gathered together into a cable and come around to this switch. So let's take a look at the schematic for that. This is all it is. This is the red pin jack that you see on the top, and then there is a switch that can select one of, actually a total of 12, but I'm only wired to 8 connections. And each of those connections is made to a particular pin on that octal adapter that you saw. So what you can do is connect a meter to this lead, and then by setting this switch, that meter is then automatically connected to each of the pins of the octal tube socket. So the nice thing about this is you can move this from one place to another in the radio and take all 8 readings by just rotating this switch. Let me give you an example. We'll turn on our new meter, and we're set to pin 8. Let me turn off some lights here. Well, that's not working. Well, let me do this. There we go. All right, that's voltage. Let me go to resistance. And notice that it reads 155.7 ohms. I hope you can read that. on pin 8, we go to pin 7, and you see it reads 38 ohms or 38.7 ohms and so on. So what I'm going to do now is go through each of the tubes in this radio using this box, collect all the resistance data, and use that to fill out a form like this. At that time, when I begin doing the actual capacitor replacement, if there are any resistors nearby that also need to be replaced, I'll know which ones and I'll know to replace those at the same time. Well, magically, I have filled in all of the RCA 1064 values for all 8 pins of all 5 tubes. And I'm now going to go through this, comparing it to the schematic, and just as I did in the Watterson radio, I'm going to make certain assumptions or conclusions about where I need to do further testing. And by the way, thought I would also refer to this. I'll zoom out so you can see it a little better. What I have also done is printed out a larger version of the schematic for this unit. And basically what I do is I print out sections and then paste them together using tape, so that I have a rather large schematic that's easier to work from than the smaller one. And so what I will be doing is now comparing this schematic to the resistance readings I got and see if there are any conclusions I can reach about issues that need to be addressed. Okay, a couple of things that I noticed from looking this over this set of resistance readings. Initially, I had an open filament string, and the cause of that was the 12SK7. The filament was open, and I'll show you how you can test that particular tube here in a second. If you don't have a tube tester, you can still check the filaments of these tubes using an ohm meter. Second thing is, I found that the pilot light was open. It should read 4 ohms, and it read infinity, and I'll also show you that one. And then finally, that R4 is the high value. Now, what is R4, and how did I determine that? Well, R4 is this resistor. It should be a 3.3 meg. And if I zoom out a little bit here, you can probably see that this end of that resistor goes up through this transformer and eventually goes over to pin 4 of the 12SQ7. So from pin 4 of the 12SQ7, that's my meter beeping at me for ignoring it. I'll just turn it off. So from pin 4 of the 12SQ7 down through this, which is relatively, this should only be a few ohms, and then to ground through this volume control should read about 500K. Pin 4 of the 12SK7 comes down through a similar winding to this end of R4, which then goes to this same point that connects up to R4 to pin 4 of the SQ7. So it should read about 3.3 meg higher than this point. So if we look at this point, which is pin 4 of the 12SQ7, may be a little hard to read here, but pin 4 of the SQ7 reads 470K. So that means that the volume control, this is a little low in resistance, or at least it reads low. But then if we look at pin 4 of the 12SK7, which is the one immediately above it, you see we get 5 meg. Well, if we add 500K, which is basically a half a meg, to 3.3 meg, we should get about 3.8 meg. So in other words, certainly less than 4 meg. And since this one actually reads low, it should be even lower than that. So it should be about 3.5 or 3.7 meg on pin 4, and instead it reads 5 meg. That tells me that R4 has probably gone up in value, which is typical for the carbon resistors that are used in these receivers. Okay, so now how did I determine that the 12SK7 was bad? Well, what I did is when I had the tester connected to the socket for the 35Z5, I can check from pin 2, and by the way, here is a little trick that it's just one of these things that you realize. You remember that I always cut the cords off of these old radios because I know I'm going to replace them with a safer polarized cord. But remember that those points, the ends of those wires that come out here, are still perfectly good test points. So if you put one end of the meter here and you put the other end on the chassis, what you should read is the resistance through this tube, through each of these tubes, and to ground, which is about 130 ohms or so. And instead I read infinity. Now, there are lots of possibilities. As I pointed out in an earlier video, any one of these tubes, filaments being open, will cause that, will break that string. Similarly, if this half or this side of the 35Z5 filament is open, notice the 35Z5 is tapped, but it's not actually tapped in the center. I'll talk about that in a second. But from this side through the 35Z5 and then through all of these tubes, which are all the other 4, you should get something over 100 ohms, but certainly less than 150 ohms. Well, I got infinity. So then I began pulling each tube individually and checking its pins. Let me show you how you do that. Here is a tube with, let me move the light around a little bit, maybe get a little better view on it. If you put the keyway facing you, then pins 2 and 7 will be this pin and this pin. Now, let me lay the meter over here next to the tube so that you can see it as I measure from 2 to 7. And you see I get no reading whatsoever. Compare that with this tube, which has the same arrangement, and I go between pins 2 and 7. Well, if I can get it to stay on there. And you see I get about 1.9 ohms. So the filament in this tube is good. This is a bad tube, by the way, for other reasons. And the filament in this 12SK7 is bad. So what I did is I pulled this one, kind of wish it had not been bad because it's a beautiful RCA Victor, and the lettering on it is very crisp. That's often the case. You know, if it's a good-looking tube, it doesn't work. So I put that into my stock of tubes that I've found bad in the last couple of months. You can see there's quite a few. There's this one has gone to air. Notice the white powder on the inside there, and so on. Every tube in this little butter dish is a bad tube in various ways. A couple of them have open filaments. A few of them have almost no emission. Some of them have shorts between elements. But at any rate, you see, actually, tubes do go bad. Some of these, by the way, this tube is a tube out of a color TV that I worked on recently. I don't tend to do videos on TVs, but this came out of a color TV. It's called a Compactron. Anyway, it doesn't matter. The whole idea is that when you work on a lot of stuff, you wind up with a lot of bad tubes. But in general, tubes are good. Most of the tubes in these old vintage sets you'll find are pretty good. Are good tubes. They may be a little weak after being operated for a long time, but don't assume that a non-working vintage set is because it has a bad tube. Probably only about 20% of the bad sets are because of a single bad tube. Most often, the problem is capacitors. Okay, now what I'm going to do is zoom out a little bit and take a look at this nice big schematic that I put together and kind of give you an overview of this radio. What I'd like to do is go over just kind of the basic idea of how this radio works. Now, down in the lower right-hand corner is the power supply, and we'll talk about that last. Up here is the converter tube, and if you watched my previous videos in this series, you know that its purpose is to convert the RF signal that's picked up on this loop antenna and convert it into an IF signal. So, for example, if you're receiving a station on 1000 kilohertz, then it has to convert that 1000 kilohertz to 455 kilohertz, which is where this transformer is tuned. It does that by putting a little transformer in part of this tube that causes this tube to oscillate. It oscillates at a frequency which is 455 kilohertz higher than the frequency you want to listen to. Those two signals get mixed together in this tube, and the result is a series of signals, one of which is the intermediate frequency. That then gets picked up and amplified by this tube. Then it passes through another IF transformer, which once again picks out the IF frequency and the sidebands on each side and nothing else, applies that to the detector. The detector converts that IF signal to an audio signal. The audio signal then comes through the volume control. It is developed by what it does is it rectifies the current that's flowing in the secondary of this transformer down here through the volume control, and then you pick off a part of that, depending on where the volume control is set, and apply it up here to this other part of this same tube, which is the first audio amplifier. That amplifies the signal. It gets transferred over to the output tube. The output tube multiplies the power and matches through the transformer the speaker impedance, so that the audio that was created here is amplified once, amplified twice, transformed, and put into the speaker. Now, let's talk about the power supply, because all tubes need a source of power. Usually that power has to be a filtered DC, that is direct current. This is the way that happens. The line voltage comes in and is applied to this end of the filament, flows to the center. And remember I said earlier that this is not actually the center tap? This side has only enough voltage across it to run the pilot lamp. Notice that the pilot lamp is connected here, and the other end of the pilot lamp is connected there. So the pilot lamp is actually connected across those two pins. The current from the line flows through this filament, and it also flows through this pilot lamp, and then eventually flows out the other side and down to ground. Ground, of course, is connected to the other side of the switch, so when the switch is on, it flows from ground up through the switch and back out to the power station, or the squirrels running the treadmill, depending on your point of view. But at the same time, notice that pin 3 is connected over here to pin 5, which is the plate. So so some of this current that doesn't go through the filament, it divides, and it goes from pin 3, the center, up to pin 5, and then through the tube and comes out on the other side. Now, that is positive current flow. If you're thinking of electron flow, it goes the other way. In other words, it goes from the cathode to the plate and then back this way. At any rate, what it does is it causes the cathode to assume a positive DC potential, which is then filtered with this capacitor and is applied to the various stages in the radio. This is what is often called B+. Now, one little trick that I will mention that all servicemen back in the day were aware of. Often, because of the way this circuit is constructed, if the pilot lamp burns out, that puts an extra heavy load on the filament of the 35Z5, because remember, the current that's coming in goes some through the pilot lamp and some through the filament. When the pilot lamp gives out, this filament gets overloaded, and it often burns out. Similarly, if this filament burns out, it often burns out the pilot light. So these two kind of go together. They're like besties. If one of them goes, so goes the other. And so it's common, if you see a radio that has a bad pilot lamp, you better check the 35Z5 because it may have an open filament as well. Okay, enough of that. In the next video, we'll talk more about actually troubleshooting this. Also, a little bit more about things like what some of these symbols at the top mean, and some of these measurements and other things. But we're probably going to take that up only after I've had a chance to replace most of these paper capacitors. So, as in previous videos, I hope this has been useful or at least informative. And I hope you'll look forward to some more. As you can see, I'm going to continue this series. I'm hoping that someday I'll actually get this radio working, but I'm in no hurry because I'm using it as a model to help explain things that other people have taught me over the years. And so in a way, I'm just sort of passing on from the generation before mine to the generation after mine. And I hope you're one of those. In any case, stay tuned. Have a nice day.